Welcome back, study group. Let's just dive right into it. Today, we're breaking down exactly how applied AI systems handle data processing and memory. And to make this super practical, we're going to anchor our explainer today around a really fascinating case study from our sources called GG Reports. We're going to look under the hood at the engineering that makes it possible for these agents to actually be useful in the real world, rather than just cool parlor tricks.
To kick things off, we really have to address the elephant in the room. Why does AI forget what we told it yesterday? I mean, we've all been there, right? You give a model this incredibly detailed, perfectly crafted context, and then, maybe 15 minutes later, it's like it suffers from total amnesia. It is incredibly frustrating, but it's also a critical engineering hurdle. Our entire session today revolves around how we actually solve this problem head-on using pure architecture.
So, here's how we're going to break this down today. First, we'll look at the AI memory limit. Then, data extraction with NER. After that, we'll dive into RAG and vector databases. And finally, we'll look at the shift toward modular ecosystems. All right, starting with part one, the AI memory limit. Right now, most of the big models operate with context windows somewhere between 32,000 and 128,000 tokens. Think of this context window as the AI's short-term working memory. Now, as long as you stay within that specific token limit, the agent is brilliant. But the absolute second that bucket fills up, the oldest data literally just drops right off the edge. Poof, gone. The agent loses vital context, and with it, the ability to execute any kind of long or complex task. So the big question is, how do we stop our hard work from just falling into the void? Well, that brings us to our case study, GG Reports. GG Reports is an autonomous GPT agent, but it's built with a strictly robotic personality and this unwavering, rigid workflow for creating reports. Instead of letting the model wander off and get creative, it forces this relentless validation and confirmation loop with the user. It's specifically designed to extract structured data and lock it down, persist it, before the main model's working memory has a chance to reset.
Which leads us perfectly into part two, data extraction with NER.
Okay, so what's really interesting here is NER, or Named Entity Recognition. Instead of reading text loosely the way a human might, the system scans and automatically tags very specific data points within a messy chat log or a PDF. So it sees the words John Doe and, boom, tags it as agent. It sees March 11th and tags it as date. It is absolutely crucial. It's the indispensable first step for turning chaotic, free-form text into clean, structured data. But here's the thing. NER doesn't do all this heavy lifting by itself. Our sources detail a whole arsenal of complementary NLP techniques that back it up. Take intent classification, for example. This helps automate confirmations by figuring out if the user is saying yes, asking a totally new question, or providing a missing piece of the puzzle. Then you've got topic segmentation, which uses lexical cohesion to chop massive chat logs into consistent, bite-sized thematic blocks. And of course, if you feed it a scanned image, OCR, optical character recognition, has to pull the text first so all these other tools actually have something to work with. If we look under the hood at the actual tools used to build these extraction pipelines, it's pretty cool. You see libraries like Spatie and Hugging Face handling the complex syntax and NER stuff. PyMu PDF is in there pulling text out of original documents, but I want you to notice that middle row. Vector databases like Pinecone and Chroma. These are the bridge. They take us directly to the next crucial piece of our architecture. And that brings us to part three, RAG and vector databases, the key to long-term memory. Now, the crucial point to understand here is that not all memory is created equal. For an AI agent to be truly useful, the architecture actually has to separate things out. You have semantic memory, which is basically the static database, who the user is, their role, the core rules of the system. Then you have episodic memory. This is about time and events, what was discussed yesterday, what specific tasks were just assigned. Teaching the agent to distinguish between these two drastically improves its intelligence. It means it can do automated follow-ups without annoying the user by re-asking basic stuff it should already know. Enter RAG, Retrieval Augmented Generation. Honestly, this is the star of the show. Think of RAG as a massive, ultra-organized, long-term filing cabinet for our language model. Instead of relying on what the model kind of sort of remembers from its initial training or relying on that super fragile context window, RAG forces the AI to actively consult an external, constantly updated knowledge base before it generates a response. It is literally the most effective cure we have against those dreaded AI hallucinations. Let's actually walk through how this RAG workflow operates, step by step, because it's highly foundational. First up, we take giant documents, like huge old reports, and we chunk them into small, manageable pieces. Second, we run those chunks through a model to embed them, meaning we convert them into mathematical representations, or vectors. Third, we index them into our database to keep everything perfectly organized. And fourth, the magic step, when the agent needs context, it retrieves the vectors that are semantically closest to whatever the user is asking and injects just that specific info right into its working memory.
And where does all this immense retrieval power live? Right here in vector databases. Tools like Pinecone or Chroma let an agent search for relevant passages across hundreds of past reports, but they only pull out the absolute most important pieces. That way you get the exact historical context you need, but you don't overload that working memory window we talked about earlier. You effectively bypass the token limit completely just by giving the AI an external brain. It's a massive game changer.
Finally, part 4, toward modular ecosystems.
For AI automation to actually survive in a real enterprise environment, a clunky monolith just won't cut it. It requires a scalable architecture. Our sources heavily emphasize modular builds. For instance, if GG Reports has a module for daily reports, engineers can just clone the core logic to create one for monthly reports. Plus, generating the outputs in structured formats, like JSON or XML, isn't just a stylistic choice. It's a strict operational necessity. It allows for seamless integration so that other agents in the ecosystem can consume that data instantly.
And that paves the way towards something super exciting: shared memory. Imagine a scenario where multiple AI agents are teaming up. If they don't have a common persistent memory, it's a disaster. They'll end up asking the user the exact same information 5 different times. But by implementing a shared memory buffer where each agent stores its extractions, you create this collective layer. It guarantees everyone operates under a single operational reality. If Agent A already confirmed a piece of data, Agent B just reads it silently from the shared vector database. So let's wrap up with a question for the group to chew on. We now understand entity extraction with NLP, we've totally beaten AI amnesia using RAG and vector databases, and we're even connecting multiple agents through shared memories. With engineering foundations this solid, what is the actual limit for graph-based multi-agent collaboration? How exactly is this collective memory going to redefine the automation of our most complex daily workflows? Take that question with you, keep analyzing these incredible systems, and I'll see you in the next explainer.